time I stop talking, you don't have to start talking. You're like, what happens to get this started? We'll just so. Or you can stop talking while I'm talking. That's all right. Yesterday, we started off talking about classification of matter. So we answered that first question, right? What is matter? And in order for something to be matter, you have to have two things, right? Mass and volume. Okay? And we talked about states of matter, right? Solids, liquids, and gases. We will definitely talk more about solids, liquids, and gases next week when we start talking, or actually tomorrow, when we start talking about kinetic theory, and why things are solids, liquids, and gases. We'll go from there. Okay? Then, towards the end of the period, we started talking about these two things, this sheet of aluminum foil and this sample of salt. And we said that both of these fall into one category of matter that we call pure substances. Okay? There are two types of pure substances that we talked about yesterday. What are the two types of pure substances that we talked about? Compounds and elements. So what makes something an element? How many types of atoms does it have? One, right? It's the same type of atom throughout the whole sample. Then, the other type of pure substance, called a compound, right? Two or more, and what has to be true about those two or more atoms? Chemically bonded, right? So, when we chemically bond those two atoms together, they become something new. They're a completely new substance than they were when they were separate. Okay? Good there. Okay. We call both of those pure substances because they have exactly the same composition. No matter where we take that sample from or how big of a sample we take, it's always exactly the same thing. It's either one type of atom or it's multiple types of atoms, but those atoms are bonded together in a specific ratio. Okay? Yes? Composition is what it's made out of, right? Like what type of atoms or what type of molecules that it's made out of. Okay? So something that's an element always has the same composition, the same type of atoms, right? Something that's a compound might have different types of atoms, but they're bonded together the same ratio, so it's always NaCl is always one Na and one Cl joined together, right? So the composition of NaCl is Na and Cl. Good? All right. So next, the other type of matter that we talk about is called mixtures. Okay? So, definition of a mixture, it says a combination of more than one pure substance. If you look back at the definition of a compound, it starts exactly the same way. A combination of more than one pure substance. But the one part that we don't have in this part in the definition of a mixture is the what? The chemical bonding part. That's the part that doesn't show up here. Okay? So in a mixture, the two pure substances that make up the mixture don't lose their identity. They don't lose their properties like what happens when we have a compound, right? So let's take a look real quick at an example of something that we did a ton of times, right? Actually, you know what? I'm going to do this for you. Here's a little video for you. No. All right. So this is a reaction of iron with sulfur. Okay? And I'm going to pause this. All right. So, getting back here. Okay? Combination of more than one pure substance, but those substances tend to retain those properties that they started with. Okay? And one other thing that separates mixtures from compounds is that when we look at the composition of a mixture, what it's made out of, it's not always the same throughout the whole mixture.
you look at different parts of that mixture, you'll see different combinations of stuff. So, 2 examples. 1, you go to the beach here, like on Lake Erie. What passes for a beach on Lake Erie? Okay, you know, it's not like the Bahamas or anything like that, but you know. Okay. If you take a handful of sand, or what passes for sand here on Lake Erie, right? Okay. Dirt, but it's got like some rocks and some seashells and probably some garbage too, you know, okay. So you take a handful of sand, you look at it, it's a mixture. Clearly you can see that there are different things in there, and those things have their own properties. Dirt, rocks, sticks, seashells, whatever else might be in there, okay. Pop cans, right, okay. Glass, you know, lots of syringes maybe, you know, whatever. So, okay. If you walk down the beach a little further and you take another handful of sand, you might see rocks, stones, glass, dirt, sticks, seashells, syringes. But are they going to be in the same ratio that they were in the first handful that you took? Not necessarily, right? Different compositions for different parts of the beach. Okay? If you go to Edgewater, like where they have like the beach, you know, it's a lot different than the beach at like Huntington, right? You know, so Edgewater is like downtown, big beach downtown. Like, so there's a marina there. They have big fireworks display on 4th of July and stuff like that, you know. So, but anyway, but it's still sand, but the composition isn't always exactly the same. Okay. The other example, chocolate milk. Right? Milk, chocolate syrup. If you put them together, right, they still taste like milk and chocolate. Yeah, they're mixed, but chocolate syrup tastes like chocolate whether you mix it with milk or whether you don't. It's diluted out, but it's still chocolate, right? But we also discussed that if we let chocolate milk sit for a while, what starts happening to it? It starts going to the bottom. Is the bottom of the carton still chocolate milk? Yeah, is it the same chocolate milk as the top, though? Not exactly, right? So those are mixtures. Yes, they're more than one pure substance. Not that chocolate milk is definitely an element or anything like that. But they're mixtures of things, but they keep the properties that they had before. When we look at mixtures, there are 2 types of mixtures. And this is letter D and letter E on your outline. So, first, we talk about heterogeneous mixtures versus homogeneous mixtures. And sometimes homogeneous mixtures go by the name of solutions, right? So letter D is heterogeneous, and then letter E is homogeneous / solution. Because you know English, you probably can tell me about heterogeneous and homogeneous solutions. What can you tell me about heterogeneous solutions? Different, right? Doesn't have a uniform composition. A uniform composition means that it's the same, right? Our sand in the example that we just talked about a couple minutes ago is definitely a heterogeneous mixture, right? It's got different parts and different things, and you can tell those different things apart. But a homogeneous mixture or a solution sometimes is confusing. Very good. It's the same, right? Sometimes homogeneous mixtures can be tricky, right? Because they look the same all the way throughout. So sometimes it might be hard to tell them apart from a pure substance. Are you just stretching?
No, actually.
Do you have a question?
Yeah.
Go ahead.
What do ketchup be heterogeneous?
Ketchup is heterogeneous, especially if you let it sit for a while. Okay. Let's talk about another. So let's talk about one that's maybe a little bit more tricky, right? Kool-Aid, right? Like if you make Kool-Aid or if you make lemonade or something over the summer, right? Or now, whatever. Okay? Kool-Aid is a mixture of water and Kool-Aid mix. if you mix it together really well, you can't really tell the difference between the water and the Kool-Aid mix. They're so well evenly distributed that you can't tell the difference between them. And Kool-Aid doesn't separate, right? It just looks like Kool-Aid. But the powder that you mix in, before you mix it in, what does it taste like? It's usually sugary, right? If you have like the not, sometimes you have to add sugar to Kool-Aid, but if you get like the packet that you just dump in, right? It's got sugary and it tastes like whatever flavor you want it to taste like, right? When you mix it into water, it's still sugary and it still tastes like whatever flavor you want it to taste like. It's diluted down, but it still has those properties. Does that make sense? So sometimes homogeneous mixtures can be tricky. When you shake up ketchup in the bottle, you can't really tell the difference between one part or the other part, but because it tastes like tomatoes and salt and vinegar, which is basically what ketchup is, right? You can still taste all those things in there. A little sugar too, because ketchup has that sweet taste to it. You know? Does that make sense?
Yeah.
So even though something looks the same, it's not always, that doesn't mean it's a pure substance, right?
So like seawater, would that be like, if you let that sit, the salt will start to drop?
So lake water, right? Let's go with lake water, because seawater is a little tricky, okay? Because if you get water from the ocean, some of it will separate, but some of it won't, right?
Yeah.
Like the dirt and the stones and the sand that's in that'll separate. But if you let ocean water sit on the counter, let's say you go to the ocean, you get a jar of water, you let it sit on the counter. Some of it will separate, but if you tasted that water, it would still be salty. The salt doesn't separate out it. So the salt water is a homogeneous mixture, but the ocean as a whole is a heterogeneous mixture because it has other stuff in it. Does that make sense? Okay. All right. So are we good on homogeneous mixtures? There are two types of heterogeneous mixtures that we talk about. Oh, sorry. Picture. Okay? One of those circles, or one of those samples represents a homogeneous mixture, one represents a heterogeneous mixture. Talk to the person next to you, decide which one is which, then we'll talk together. Go. Which one's homogeneous, which one's heterogeneous?
Both of them are heterogeneous, you can tell the different parts of it. Both of them are heterogeneous, you can tell the different parts of them. It's
True.
not,
No.
neither of them
Does
look like they're
does it have a consistent composition? Is there one part on the one on the left that has more circles than squares? Other than like, an actual circle. The circles are pretty evenly distributed, and the squares are pretty evenly distributed, right?
Yeah.
That's the characteristic of this mixture. Is it perfect? No. But do you get the idea? Alright, let me talk. Alright, so which side is a better representation of the heterogeneous mixture? I would say the right is a better representation of a heterogeneous mixture. Okay? There are two things that make up this mixture, right? Circles and squares. Are there parts on the right where there are more squares than circles? Are there parts where there are more circles than squares? Sure. The one on the left is probably a better representation of a homogeneous mixture. Okay? Are the squares and circles evenly distributed on the left? Pretty much. I mean, okay, could it be better? Maybe. All right, but it's better than the one on the right. Okay. Are either of them? So let me ask you this question: if I wanted to make the one on the left a compound, what would I have to do?
Light on fire.
Well, yes. How would I change the picture to make it a compound?
Make them all try.
What has to be true about the circles and the squares, Kat? They have to be bonded. So what would you do with them?
Triangles.
Put them together, right? Okay. I suppose you could make them triangles, all right? So, to represent you've made something new. But if we represent that they're just bonded together, let's just put them together and we go from there, right? Okay. So, heterogeneous mixtures. Heterogeneous mixtures come in two forms. The first is called a suspension. A suspension is made up of large-sized particles. And one of the characteristics of a suspension is that those big particles will separate themselves rather easily based on their size, or you could also throw in there based on their density. Say again? Well, we'll get to that in a second. But all right, Italian salad dressing. When you pull Italian salad dressing out of the refrigerator, what does it look like? Oily on the top, vinegary on the bottom, right? It's got two layers in it when you pull it out of the fridge. Okay? So, you shake it up, and it mixes itself all together, but eventually what does it do? Separates back out. Italian salad dressing is a suspension. The particles, namely the oil and the vinegar that are mixed together, are so much bigger or different in size from one another, density as well, that they will separate themselves out by themselves.
Oh, okay.
Making it colder, actually making it warmer, decreases the density of the water, so it's actually a little bit easier to mix them together when it's warmer. When it's colder, they're different in density.
I know.
So,
When it's in the refrigerator, it separates slowly.
they don't move quite as much, so yeah. So, we talked about a little while ago, Devin, if you went to the ocean and took a jar of water, right, put it down on the counter, the stones and the rocks go to the bottom, the sticks float to the top, right? That's a suspension too.
What if you like boiled it? Would it separate them?
It would, but so you can see this sometimes if you boil even tap water, but if you boil salt water, put it on a pot in the stove, boil it. Do you know what eventually you'll have left?
Hot salt water.
Hot, except what's going to happen to the water? So what's going to be left in the pot? Just salt, right? But boiling is pretty easy to do. So that's separating a homogeneous mixture. It's a little bit harder to do than just sitting it on the counter and letting the big and the small stuff separate. What? Well, salt water is a mixture of what? Sodium chloride, right, and water. Do those have the same boiling point? Water will boil at a much lower boiling point than salt does, so the water boils off, but the salt is left there. Okay? So we separated it. All right, the last type of heterogeneous mixture is called a colloid. Colloids are tricky. So, based on the definition, it's a mixture of smallish particles. Okay? So, how does that make it different from the other two? Well, things don't separate, but because the particles that are mixed together are kind of biggish, but kind of smallish, medium, right? It prevents light from passing through. And we've talked about that before. When something prevents light from passing through, what does it look like? It could look solid, it's like cloudy, right? Like with the precipitate. Does that sound familiar? Right? The precipitate has the particles in there so the light can't get through and it looks cloudy. So here's an example of a colloid. Ready? Fog.
What about blood? Why?
So blood's more of a suspension because you have like the cells and stuff like that. They're pretty easy to separate. So, all right, let's think about fog or clouds, right? What are clouds made out of? Water, right? But they're also mixed with what? Air. Okay? The particles of the water condense to a point that light can't get through, and that gives it that cloudy look. Okay? But if those water droplets get bigger and bigger and bigger and they congeal together more, what happens? It rains. Rain is a what? Rain is a suspension. It separates itself out, right? The water falls out of the air and falls to the ground. Okay? Good there? All right, here's another colloid, and this one's tricky too. Okay? So, back in like second grade or wherever, did you ever go on a field trip to Hale Farm? Yeah. You go to Hale Farm, right?
Did that like last?
Some people, I said sometimes you go. Yeah. Anyway, some people hate Hale Farm. Some people love Hale Farm. Right? My kids.
When we went,
My kids love going to Hale Farm. Like,
They got really took out, and then they were like, okay, it's over now. And we're like,
we went for like a slave type thing, and like it's very intense, like, very scary. They like take shoot. We went there. It was very clear that they had changed it from what it was previous, or what the teachers had said it was, to a very much of, we don't want to get sued.
all right.
It made it very boring.
That was when we go to church and then we had to pretend to lie.
So, if you've been to Hale Farm, or if you've been somewhere else like on an actual farm, have you ever seen anybody like actually milk a cow before? Or maybe seen like a video of somebody milking a cow? So, anyway, when you get milk straight out of the cow, okay, and you let it sit in the bucket or the or bin or wherever you put the milk in, okay, do we know what happens to the milk? So,
It's really bad.
hold on a second. Let me finish my milk story.
It hurts.
So,
and it gets,
all right,
smells
so
like death.
milk,
I left the milk carton in my dad's.
milk, when you get it straight from the cow, separates on its own. Not exactly. Milk is a combination of fatty things and watery things. And the fatty things go to the top, and the watery stuff goes to the bottom. So, well, you take the fatty part off the top, and what do you make out of it? Butter, cheese, ice cream. Like that's why those things are delicious, because they have lots of fat in them. All right. Whether it's healthy for you or not, it's still delicious. All right. But wonder why those outlines aren't filled in, Jafar.
Yeah.
So
I'm checking.
so. All right.
I know. Yeah, but mine's filled out.
So,
Mine's filled out too.
I didn't say it was
Never
just
said
you.
yours wasn't filled out. I'm saying mine is.
All right.
We're not gonna pass.
So, milk on its own will separate out, but when you buy it at the store, you don't want it to like, you don't want milk in your fridge to like separate out, right? So we don't want that, okay? So, milk goes through a process at the plant that prevents it from separating out. Okay?
I heard somewhere that Sydney salami, like they let mold on it and then like scrape them all.
Salami? We're talking about milk. Let me finish the milk story.
It's milk.
So, by the way, salami is definitely a suspension. You can see all the little fatty parts in the salami. So, all right. So, if you read the size of a milk, or if you read the side of a milk jug, right? It says that the milk is homogenized. Okay? So, because you know English, right? Homogenization means you're doing what to something?
Something else.
Making it the same, right? Preventing it from separating out. What they do at the milk plant is they take the fatty part of the milk and they put it through a process to break up the size of the pieces of the fat. So they're closer to the size of the watery part, and that prevents it from separating out. But they also can change how much fatty part is in your milk. Like 2% milk is how much fat? 2%. Skim milk is 0.5%. Fat-free milk is basically water. Like, yeah, that's like, you know. So skim milk is like 0.5% fat. 1% milk is 1% fat. Whole milk is like 3.5%. Okay? Yeah, basically, like, you know, so, but anyway, one last thing, so you can change the percentage, but by making those fat molecules a little bit smaller, you keep them from separating out from one another. Okay? One last thing on milk. Anybody ever had Hartzler's chocolate milk? Oh. So they usually sell it at like Heinen's. They might sell it at Whole Foods. So first it comes in like a glass bottle.
Yeah.
But it's like it's whole milk, but it's chocolate milk. So it's like, but it's basically drinking like a melted milkshake. So all right, so suspensions, colloids, solutions. All mixtures all retain the properties that they had before, but depending on the size of the particles, sometimes they're easy to separate, sometimes they're not. Okay? Good there.
What was the story with the chocolate milk?
Well, first we talked about the chocolate milk on its own will separate, so it's a suspension. Okay? But I just wanted to bring up the idea like the Hartzler's chocolate, it's like whole milk. It's just like really, it's just good. So it's expensive, but it's good. Because we were talking about milk. So you know how sometimes you like turn to Maddie and start talking about unrelated things to class?
Yeah.
That's kind of what I just did.
It's been great then, so I mean it's somewhat related.
I mean, it is Thursday. It is Thursday after all.
GPA great.
Yes, Ronnie. Milk after it goes through the homogenization process. Hey.
So is it like
Colloids.
Is it like harder for it to get mixed together again? Or is it
It's harder for it to separate back out. That's really, but it's not clear. Like salt water is real clear. That's a solution or a homogeneous mixture. Milk looks like one thing, but because it's cloudy, that gives it the colloid. Okay? But big things like Italian salad dressing, big particles, they'll separate on their own. Like you can shake them together, but they'll separate on their own pretty easily. Does that make sense? Okay. All right. Do you guys want to talk about properties? Or want to talk about changes first?
Properties.
none of the above?
Well, I mean, you pretty much know changes. Like we could seriously go through changes in matter tomorrow in like 10 minutes because you guys can know all that. There you go. All right. You trust me.
What is that like?
All right.
Solids to liquid and stuff like that?
Physical changes, chemical changes. Yeah. All right. So properties. First, we talk about intensive or characteristic properties. Intensive or characteristic, we can use those two words interchangeably. Intensive or characteristic properties are things that don't depend on the sample size. Okay? 1 grain of salt or a spoonful of salt will have the same characteristic properties. It doesn't change depending on the sample size. And there are 2 types of characteristic properties, chemical properties and physical properties. hopefully those two words, you've seen those before in your lifetime. All right, so let's talk about chemical properties first. Chemical properties. How does this substance react when it's placed in certain situations? How does this substance react when it interacts with other substances? Basically, chemical properties tell us about the chemical reactions of a substance. Will it form, say again? Yeah, I think that's what it's like, yeah. So you have the beginning of them in A and B, right? Yeah. I wanted to make sure that you had them on, I thought I gave this to you. That's what chemical properties tell us about. Now, the tricky part about a chemical property is this. Here's a chemical reaction up on the board, one you've seen like 10 times in the past couple weeks, right? So, it isn't balanced, that's correct. So,
You put 2 in the MgO, 2 in the MgO.
that wasn't the point of that equation, but I'm glad you guys brought it up. So, yeah. All right, is everybody happy now? We good? So, can we discuss this further now that we know that it's balanced? So, all right, so chemical properties. We want to know if magnesium reacts with oxygen. So we test it out and we find out that yes, magnesium does react with oxygen. But one of the kickers is, if you want to find out if magnesium reacts with oxygen, you have to test it. And when you're done testing it, you don't have magnesium anymore, right? You've got magnesium oxide. So when we test chemical properties, we actually have to change the substance in order to test it. Okay? Composition of the substance will change when you check the chemical properties, because you're basically checking whether it reacts with something else. And if it does react with something else, then you don't have that substance that you started with anymore. Good.
And you're also like not reverse the chemical.
Let's go, instead of not reversing, how about it's more difficult to reverse a chemical reaction? Because remember, right, magnesium and oxygen react with each other to get to a lower energy state, right? Could we separate them back out?
Well, if you like run out of one.
Well, but still, this here, magnesium and oxide joined together, is a lower energy state than these separate. Could we separate them back out? Yes, we just have to give them energy, right? We have to put energy into it. It won't happen on its own, but we can make it happen, right? So that's why when we talk about chemical changes, right, you learn chemical changes as things that can't be reversed. Well, that's not true. We can reverse anything if we have enough energy to do it. Does that make sense? Yeah. It won't happen on its own, but we could make it happen if we wanted to. All right. 2 chemical properties that we talk about, flammability and reactivity. Flammability is a fancy name for, whether it's something flammable, catch on fire, which we learned in our last unit is what kind of a reaction? Combustion reaction, right? So flammability is basically asking, does it combust? Is it combustible? Does it react with oxygen? Okay. All right, good there? All right, next, physical properties. Physical properties, you don't have to change the substance in order to measure them. The characteristics of a substance that do not result in a change of that substance. All right. Do not result in a change in substance. You told me you knew that. All right, so here is a list of physical properties. Here's a list of physical properties. So, these are not all of the physical properties that are out there, but they are some physical properties. Go ahead and write them down. And then if you need some explanation about any of them, we'll talk about them in a little bit more detail. I think you probably know most of them.
first one.
All right, so viscosity. Viscosity is how thick something is, or how easy it is to get it to like pour. Things like ketchup, honey, molasses, they have a real high viscosity.
It's like for
Resistance to flow.
What does malleability mean?
Malleability is the ability to turn something into like a wire. So like certain metals we can turn into a wire, like copper and gold and stuff like that, but certain metals we can't.
Pretty much bending, right?
Bending.
So like Play-Doh?
Play-Doh, yeah, generally though we talk about it in terms of metals, but Play-Doh is pretty, yeah, Play-Doh is malleable, definitely. All right, and then the last one, density. I hope you guys, I got the impression you guys know pretty much about density, yes?
Yeah.
So let's finish off the backside. All right, so density. Density is a ratio between two measurements, right? Right. Density is the relationship between mass and volume. So on the backside, little I, D is equal to mass over volume, right? It's the amount of mass per unit volume. That's how we define density. Or how much stuff are we trying to slam or cram into this space?
I like the
So we talk about density in terms of matter, but we also talk about density in other arenas, in other applications too, like population density. Right? Where generally is the population density the highest? In cities, right? We have more people and less space. Like Beijing, Hong Kong, Tokyo,
China in general.
those kind of places. Okay? But then, right? Good there? So this picture that shows up on the back page is a density column. 4 liquids, 4 solids, 1 gas. All right? So, highest density is steel. Where is it in this column? It's on the bottom, right? Lowest density is air. Where is it? Top. So where do less dense things go? Less dense things go up, right? More dense things go to the bottom. That's how Italian salad dressing separates itself. The vinegar is more dense than the oil. So the oil goes to the top and the vinegar goes to the bottom. Okay? All right, good there? All right, so tomorrow we'll go over changes in matter quickly at the beginning and you will have your quiz right after.